Okay guys, I'd like to look at this problem together. This problem is arc tan 3x dx. You had a similar one on your homework last night. Your homework was, I think, arc sine of something. I'm not sure what, but arc sine of something. And this is done the same way. This is actually an integration by parts problem. It looks like it's on your formula sheet, but you can look on your formula sheet. It is not on your formula sheet. There's no integration of arctan on your formula sheet, just like there is no integration of ln of x dx on your formula sheet. And so both of these problems are done by using integration by parts. This would be u and this would be dv. On this problem, this part would be u and this part would be dv. And both of these problems are something that looks like they should be on your formula sheet, but they are not. So please make sure that you know how to do these problems, and there definitely will be something like this on your quiz on Wednesday and or on your test next week. All right, so please make sure you know how to do these integration of arctan, integration of arc sine, and the ln of x. Now, be careful. While these two are actually integration by parts problems, this problem is a regular u sub problem, okay, not an integration by parts problem. And that's because if you make u equal to ln of x, the derivative of ln of x is 1 over x. And so there really is a 1 over x here that's going to cancel out. So therefore, this over here is a u sub. But if you have this ln of x without the divide by x, it is an integration by parts problem. Let's go back and look at this arctan. Okay, if u is equal to arctan 3x, then my dv is equal to dx. And I do the crosshairs here. On this side, I'm going to take the derivative. The derivative of arctan 3x is actually u prime over 1 plus u squared, where 3x is my u. The derivative of 3x is 3, and then you put 1 plus, if u is equal to 3x, then u squared is equal to 9x squared, and don't forget the dx, because remember the dx was down here, but then you multiply both sides by dx, so the dx comes over onto the right side. On this side, the integral of dv is v, and the integral of dx is x. So the answer for arctan 3x dx, the integral of that, if I'm putting it into an integration by parts problem, is uv minus the integral of v do. My uv is actually these two top columns multiplied together, or the top row multiplied together, and then the diagonals here are the VDUs. Okay, so if I multiply the u and the v, I get x arctangent 3x minus the integral of 3 times x over 1 plus 9x squared dx. And if I can just find this integral, that would be the answer, the sum of these two terms to this problem. How do I find the integral of 3x over 1 plus 9x squared? Is that an arctangent problem, or is it a regular u substitution problem? Well, let me try u substitution first. You should always try u substitution first, okay? So what I get is du dx equals 18x, so therefore dx is du over 18x. I substitute two things. I substitute my u, and I substitute my dx. So that gives me the integral of 3x over u times du over 18x. Do my x's cancel out? Why, yes, they do. So this turns out to be a regular u substitution problem. And the answer here is 1/6 ln of u plus c. And that's a great answer. It is just the wrong answer. Okay, so I want to go over here and let me just rewrite the whole answer. The whole answer is x arctan 3x minus the integral of this, which is 1/6 ln of 1 plus 9x squared plus c. All right, let's do another problem. This problem here, okay, how would you do this problem? Okay, you want to do the table trick? If you say it's a table trick, then what you're saying is that this is a PE or a PT problem, which it is. So on the left side, I put x. On the right side, I put ex squared. On the left side, I take the derivative all the way down to 0. On the right side, I take the integral, okay, of this. And when I take the integral here, is this what I get? right? You just divide by the derivative of x squared. This is actually wrong. Why is this wrong? Because the integral of ex squared, that's e to the u, okay, is actually equal to e to the u divided by the derivative of x squared, which is 2x, and your x's need to cancel out. And they do not cancel out here, which means that this is not how you take the integral of e to the x squared. Your x's did not cancel out. So none of these down here are correct either. All right, so the table trick problem does not work in this situation because the integral of ex squared dx cannot be done with u substitution, where x's do not cancel out. Okay, I mean, I could try it here. U equals x squared, du equals 2x, dx is going to be du over 2x. And when you substitute two things, okay, you get e to the u times du over 2x. Do my x's cancel out? They do not. So you have to come back here and say, you know what, this is not a table trick problem. This is not an integration by parts problem. What type of problem is it? Yeah, I should have done u substitution first. Remember, guys, you always start with u substitution. Okay, if that doesn't work, then you move to integration by parts. But if you jump to integration by parts, you might have missed just the easiest way to do this problem. So let's think about this. If I think that this is an EU problem, that would be my u, okay? X squared. When I take the derivative of both sides, okay, then what I need to do is replace two things. I need to replace my u and my dx. Well, let me go ahead and replace that. Okay, do my x's cancel out? Well, yes, they do. So this actually becomes 1/2 EU du. And what is the integral of e to the u du? It should be something that's an easy reverse power rule problem or something on my pink sheet. And it turns out it is on my pink sheet. And that is a great answer, 1/2 EU plus c. It's just the wrong answer. Make sure you go back in and replace your u. A shortcut to this would have been, if you saw that this was your u, you could have said, okay, it's an e to the u problem, so you copy your e to the u, divide by the derivative of x squared, which is 2x. Do my x's cancel out? Why, yes, they do, and that's another way to get the same answer. Let's move to this problem here, the integral of x squared ex. And let's try the same thing with u substitution on that problem. If this is my u, I copy my e to the u. If I think it's an EU problem, I divide by the derivative of x, which is 1. Do my x's cancel out? No. So this is not an easy u substitution problem. In other words, I can't say u is equal to x, du dx is equal to 1, dx equals du. Come up here, replace two things, okay, and expect it to cancel out. Let's see, does it cancel? Do my x's cancel out? Oops, let me write this. This is not right. It should be e to the u du. There you go. Do my x's cancel out? No, they don't. So this is not a u substitution problem. Or maybe I picked the wrong u. That's possible too. But just to let you know, it is an integration by parts problem. This is a polynomial. This is an e. What two problems can you do the table trick with? PE and PT, okay? The way you do that is first you make sure u substitution doesn't work, and I did make sure of that. Then you apply your table trick. On the left side, you take the derivative until you get to 0. On the right side, you take the antiderivative. What is the antiderivative of e to the x? Well, it's e to the x divided by the derivative of x, which is 1. And do my x's cancel out here? They certainly do. Okay, so this just becomes 1 over e to the x, or 1 times e to the x. And then I take the integral again, which is e to the x. I take the integral again, which is e to the x. All right? So on the left side, I take the derivative. On the right side, I take the antiderivative. Then you put down alternating signs, start with plus. So plus, minus, go diagonal here, and then that is your answer. You just read it out. You multiply and add every multiple together. So here we go. The answer is x squared ex minus 2x ex plus 2ex plus c. And that is the answer to this integral. Now, You could have done it the long way. You could have done the integral of u dv equals uv minus v do, and you would have had to, do the u dv inside the u dv every time, maybe 2 or 3 times to get this answer. So this is a shortcut, but this way would have worked also. All right, I want to look at one of your homework questions. A lot of students had trouble with it. Let's look at number 7 and 16. Okay. Number 7 looked like this problem here. And it turns out you can do this problem 2 ways. One way with back substitution and another way with integration by parts. Okay. You get different answers, but actually they are both correct answers. Okay, so let's look at back substitution first. Okay, if I take the derivative of both sides, I'll get dx is equal to du. I replace 2 things. I replace my u and I replace my dx, and then I ask myself the question, do my x's cancel out? Why, no they don't, but something actually special happens here. This x, okay, can be solved over here. X is actually equal to u minus 1. And when do I know I can use back substitution? I can use back substitution, a lot of times I can tell, because these x's here sit next to each other. They're 2 expressions that are multiplied by each other, but they have the same power. This power of x is 1 and this power of x is 1. And so that's when I suspect it might be a back substitution problem. So what I'm going to do is I'm going to replace the x right here as u minus 1, put the square root of u right here, but that's really just u raised to the 1/2 times du. And what happens here is students get stuck. They think that this is a Lipit problem, an integration by parts problem, because you've got 2 expressions sitting next to each other. But this is where students get stuck in back substitution. Do you remember what you do here? When you get stuck on back substitution, when it looks like there's nothing else you can do, what is it that you're supposed to do? Do you remember? You can actually distribute this u to the 1/2. And what you'll get is u to the 3/2 minus u to the 1/2 du. And what we have now is actually 2 problems. You thought you just got to do 1, but oh boy, you get to do 2. And so the way this works with this would be plus 2 over 2. So you divide by 5/2, which is the same as multiplying by 2/5. You add 1, which is adding 2 over 2. You divide by 3/2, which is the same as multiplying by 2/3. Okay, and don't forget Charlie. And when you come in here, this is going to be your answer, but make sure that you replace your u, okay, with whatever you made u to be. That was something that you made up, right? And that is the answer using back substitution. All right, let's look at the same problem, but let's do integration by parts. Okay, so the same problem that we did back substitution with. I'm going to make that my u, my x my u, and I'll make this part my dv. All right, u is going to be equal to x. dv is going to be equal to x plus 1 raised to the 1/2 dx. On the left side, I'm going to take the derivative. So what I get is the derivative of x is 1 dx. And if I take the integral of dv, I get v. If I take the integral of this, what I get is, I don't know if, let me just say u would be equal to x plus 1. So what am I doing? I'm taking the integral of x plus 1 raised to the 1/2 dx. If I say u is equal to x plus 1, du is going to be 1 dx. I substitute 2 things. I substitute my u and I substitute my dx. So that's going to be u raised to the 1/2 du. This is going to be, you add 1, divide by 3/2, which is multiplying by 2/3. So the answer is 2/3 u to the 3/2 plus Charlie. We don't worry about Charlie in this problem. So the answer here is 2/3 x plus 1 raised to the 3/2. All right, so my answer, according to the integration by parts formula, okay, the integral of u dv is equal to uv minus v du. U times v are these 2 adjacent, expressions multiplied by each other. So that's 2/3 x times x plus 1 raised to the 3/2. And then I subtract v du, which is these diagonals multiplied by each other, which is 2/3 x plus 1 raised to 3 halves dx. All right. In order to do this integral on this side, I'll make u equal to x plus 1. du dx is going to be equal to 1, so therefore dx is du. I substitute two things, my dx and my u, so this becomes 2 thirds u raised to the 3 halves times the integral of 2 thirds u raised to 3 halves du, and do my x's cancel out? Why, yes, they do. So then this is going to be an easy reverse power rule. I do have to rewrite it. Let me take out the scalar 2 thirds. Okay, it should be an easy reverse power rule or something on my pink sheet. And it is an easy reverse power rule. You add 1 and then divide by 5 halves, which is the same as multiplying by 2 fifths. So this answer here is 4 over 15u raised to the 5 halves plus Charlie. And I don't have to put Charlie here right away. I just add Charlie at the end. And so when I rewrite the answer to this problem, it is 2 thirds x times the quantity x plus 1 raised to the 3 halves minus, there's that minus sign, this integral solved. So that's 4 over 15, but my u is really x plus 1 raised to the 5 halves plus Charlie. And there is another answer for this same problem. All right, let's do this. Okay, that's the area volume, right? Okay, what I need to tell you is that you do have an area volume question on your test next week, okay? And it's similar to this one, actually, okay? I'll give you another area volume problem in a few, maybe your next homework has it, okay? When you draw ln of x, you need to know this point. What is this point here? 1, 0, okay? Now, the problem says go from 1 to e. So I also have to put e here. Guys, when I put e here, what's this point up here? E comma 1, right? It's actually e comma ln of e, but ln of e is 1. So you need to know that, okay? And so what I'm going to do is I'm going to highlight the area that I'm going to rotate. It's been a long time since we've done area volume, but you need to remember how to do area volume. And area volume is an easy question to also include with integration by parts. I'm going to take this area, I'm going to revolve it, rotate it around the x-axis, okay? And what that means is you can see when I revolve this thing that it's going to be like, kind of like a big old dome on its side, right? Can you see that? All right. Do you see, does it have a hollowed out portion? It does not, okay? So your formula is going to be the volume is equal to, since you're rotating it, you know it's either r squared or r squared minus r squared. It's one or the other, okay? Is it a dx or a dy problem? It's a dx because you're rotating around about a horizontal line. Another way to say it is, let's find your r. Your r is from the axis of rotation through the region to the furthest point on the region. Okay, that's your r. Do you see that this Riemann sum bar has a dx width? Okay, so therefore this is a dx problem. Okay, so when you rotate this, I'm going to take out this little r squared because is there a little r? There's no hollowed out portion, right? If I go from the axis of rotation, not through the region, there's nothing that's not through the region. Okay, this region is flush up against the x-axis, so it's a pi r squared problem. All right, let me figure out what my r is. Let me pull it out of the board for you. I'm going to pull it out of the board. Guys, is it x minus x or y minus y? Y minus y. What's the top y on this problem? Ln of x. What's the bottom y on this problem? 0. So this is going to be ln of x minus 0, which is really just ln of x. So let me plug this into my formula. If you can just even set up this problem correctly on your test, you get partial credit. Okay, so set up the problem correctly, and now let's do the integration by parts. It is an integration by parts problem. Okay, if I had this problem, it wouldn't be. So just FYI. If I had something like this, the derivative of the derivative of ln of x is actually 1 over x, so the x's would actually cancel out. If I had this problem, it'd be u substitution. But since I don't have this factor, it actually is an integration by parts problem. Okay, my u is equal to ln of x. So let me just go ahead and do a chart. My u is equal to ln of x. Actually, ln of x squared. My dv is equal to dx. What's the derivative of ln of x squared? 2 ln of x raised to the first power times what? What's the derivative of ln of x? 1 over x. There's chain rule going on here. Okay. What's the integral of dx? x. So what you have here is v is equal to pi times this integral. Well, this integral, remember, is just going to be uv minus integral of voodoo, okay, vdo, okay. And so, guys, u times v is x ln of x quantity squared, right, minus the integral of v do. Do you see this x times this x is going to be 1? Oh, I forgot the dx there. Let me just put in a dx. It's not super important, but, notation-wise, it should be there. Okay, so this is x times 1 over x, which is 1. So in here, this just becomes the integral of 2 ln of x dx. Hopefully you saw that. Do you see what I'm doing? I'm saying 1 over x times x. You want me to put it in? Are you guys okay? Like this is 2 times 1 over x. See, it's actually 2 over x times x ln of x dx. But the 2x's cancel to 1. Okay? All right. Then this becomes pi times the integral of x ln of x quantity squared minus, oops, sorry, the integral is done, sorry. Pi times the parentheses x ln of x squared minus the integral of 2 ln of x dx. What is the integral of 2 ln of x dx? You get to do it again. Okay, so it's integration by parts. U equals 2 ln of x. Du is just dx. What's the derivative of 2 ln of x? 2 over x dx. You guys okay with that? What's the integral of x? I'm sorry, integral of dx. X, all right? So this becomes pi times x ln x squared minus what? Minus this integral, whatever this integral is. I actually need another parentheses here and another parentheses here. So regular, whatever this right here, whatever this uv minus v do is, it goes inside this bracket. It's a regular thing. It's a uv dv voodoo inside a uv voodoo. Okay, so what's u times v here? 2x ln of x minus, okay, what's v times du here? 2 dx, very good. What is the integral of 2 dx? 2x, okay, so this becomes pi x ln of x squared minus integral, or parentheses, 2x ln of x minus 2x. Hopefully that's right. That was a lot of work. Everybody good? And then be careful with your negative signs. Do you see this negative distributes to both? So this is going to be pi times, okay, this is a pi times this whole thing. Okay, so it's going to be pi times, I usually wouldn't carry down the pi like this. I'm just trying to do it just to make it clear. Usually I would just multiply by pi at the very end. Okay, but this is what I get when I distribute the negative. Okay. But I have limits on this problem. Really it's a plus c, right? Because I took the integral. But what are the limits going to go from? What x value to what x value? From 1 to e, okay? So let's come back down. So first I plug in the e, then I plug in the 1, then I slap a minus sign between. You guys agree with that? Okay, so let's do it. Because you have a problem on the test, we have to plug in e's and 1s. So this is going to be pi times, are you guys okay if can I just ignore the pi? I'm going to do this other part and then multiply by pi when I'm done. Okay, so let's put in the e. So this will be e times ln of e squared minus 2e ln of e plus 2e. All right. When I plug in the 1, I get 1 times ln of 1 squared minus 2 times ln of 1 plus 2. Then I slap a minus sign between. Okay, what did I really just do? I really just did the antiderivative plug in e minus the antiderivative plug in 1. First fundamental theorem of calculus. When I'm done, I'm going to have to try to remember to multiply by pi. Okay, guys, what is ln of e? I expect you to know for the test. What is it? 1. So that's 1. This is 1. What is ln of 1? I expect you to know that for the test. 0, and this is 0. So what I get is e minus 2e plus 2e minus 2. Okay, so then you get e minus 2, but don't forget to multiply by pi.